Okay, so you know some things about acids and bases since we've used them and we've done some stuff with them. What kind of things do you know about acids and bases? Anything? pH is a thing. Okay, so there's this pH scale with 7 in the middle. Yep, we'll talk about that. What else do you know about acids and bases?
I don't know which one it is, what acids are in.
Of what?
Of the pH scale.
Oh, okay, yes, that's correct. What else do you know about acids and bases? What do they taste like? What does that mean?
It's sour?
Sour, yeah. So sour flavors are generally caused by acids, so we eat a lot of acid. Pretty much anything that is sweet is also acidic. That's a little bit too general. But a lot of candies and drinks and other sweet things are also acidic because they tend to balance each other out really well to have acidity and to have sweetness together. Does anybody know what bases taste like? Yeah, they're usually kind of bitter or like soapy tasting. So things like, I don't know if you ever put baking soda in your mouth, like to clean out. It's gross, don't do it. But you can, and it's not dangerous or anything, and it kind of has this like bitter, soapy sort of flavor. So you don't use bases quite as much in foods. By the way, don't just drink acids and bases in the lab, but they are in foods. Yeah, Lindsay.
Oh, this is really cool. I know some out of their
Okay.
I don't know if there's
Yes, it does, because oils are generally base sensitive, so the base can break down those triglycerides into more soluble components that then can come out. But I think acid also, right? Because don't people use like tomato juice for skunks, or when skunk gets skunked too? And that's some of the acid and some of the enzymes in there that might do that as well.
Is peroxide an acid?
Not exactly. It's a little different. Yeah.
If you mix them, it helps. I don't know.
Okay.
It's useful information.
Yeah, that could be. What were you gonna say?
I was gonna say that our stomach is really acidic.
Our stomach is really acidic. That's true. Yeah, and that helps us break down foods that we break down through those means. So that's some good stuff about acids and bases. We're gonna talk first about being more careful about defining what makes an acid or a base, and then looking at some different equations and some acid-base reactions and trying to figure out what the acids are, what the bases are, and then if there's time, I don't know if we'll get to pH today, but if there's time, we'll get to pH. My pen is all tangled here. That's all right. Okay, so let's look at some definitions. Now, if you look in the book, there's two different theories of what makes an acid or a base presented. If you look in other books, there's even more than that. We're going to focus on one definition that is most useful for what we need it for, which is called the Bronsted-Lowry definition. Over the years, people have come up with different ways of defining acids and bases for what they want to use them for. Our focus this semester is in biological systems and then applying this to things like enzymes and other types of things. So this is a good definition for that. So in this definition, we say that acids are compounds that donate hydrogen ions. We'll talk about what this means in a minute. And bases are compounds that accept hydrogen ions. So acids donate hydrogen, bases accept them, different kinds of molecules. So we're going to look at a reaction, and we're going to try to figure out what is the acid and what is the base based on what is actually happening in that reaction. So let's take a look at that. So in this reaction, we have this, I didn't put the states, but it's actually a gas, hydrogen chloride, reacting with water and making these two ions, one of which is called hydronium, H3O+, and the other one is chloride. So thinking about what's happening in this reaction, going from left to right, which of the two molecules, HCl or H2O, is giving up a hydrogen? The HCl, does everybody see that? It's losing its hydrogen. How do you know? How can you tell? The H is separated. Yeah, exactly. So that's all correct. You can see that it starts as HCl, and then on the other side of the equation, the H is no longer with the Cl. So that means it is left. We can even draw that happening. So we can say the H left and instead connected over here. That's not exactly how we would draw it in a chemical context, but that works for us. So the H has left the Cl and gone over there. So what does that tell you about the HCl? What can we call it? We can call it an acid because it lost its hydrogen. It donated hydrogen, and that makes it an acid. Okay, where did the hydrogen go? To the H2O. It went from the HCl to the H2O. So what does that make the H2O? A base, right. Does that mean water is always basic? No, and we're going to talk about those later, but this idea of solutions being acidic or basic is separate from the definitions of what is an acid and what is a base. So a base or an acid is not an identity. It's not something that we say this particular compound is an acid. It's a description of a role that something is playing in a reaction. But what is it doing in the reaction? That's what determines whether it's an acid or a base. So a lot of molecules could be both, depending on what's happening in the reaction. Now, another thing about acid-base reactions is they are reversible. So instead of just going from left to right, we can also think of this reaction going from right to left. So the product's going back to form more reactants. If we're looking at the reverse reaction then, what is the acid? So starting on the right and going to the left, which molecule is the acid? The H3O, how do you know? Yeah, it went from H3O to H2O, so it's also losing its hydrogen, just like the HCl was losing its hydrogen the other direction. So this is also an acid, and that makes this the base because going backwards, it's the one that is taking the H, that is accepting the H. All right, let's look at one more. This molecule, NH3, is called ammonia. And it becomes ammonium, which is an ion that we know. And there's also hydroxide there, another ion that we know. So, same question, going left to right, which of those two molecules is acting as an acid? NH3 or H2O? Why NH3? So that means it's donating a hydrogen? So it's got to be the base then, right? Because it's accepting the hydrogen. It's going from NH3 to NH4, so that means that it is actually the base in this case. And that makes water the acid. Water is giving up its hydrogen to the NH3. So you can see here already between these two equations that acid and base is not an identity, it's an action or a behavior. The water is the base, is acting as the base in the first reaction, it's acting as the acid in the second reaction. Okay, and then to finish this up, going from right to left, which is the acid, the NH4 plus or the OH minus? The NH4 plus is the one that's giving up its hydrogen going from right to left because it's going from NH4 plus to NH3. And then it makes the OH the base because it's taking it and going from OH minus to H2O. So because of our definitions, acids are compounds that donate H plus, bases are compounds that accept H plus. That means that an acid-base reaction can be pretty easily recognized as any reaction where H plus is transferred. That's what we're going to call an acid-base reaction. And these reactions are highly predictable because they only differ by that one thing. So we actually have a special name for the products of these reactions. We can pair these up and say that those two molecules are basically the same except for the H. So they only differ by that transfer of the H. And then the same thing with these two. And the name we give to that is conjugates. They're the conjugate acid or the conjugate base. So we would say chloride is the conjugate base of hydrogen chloride. We would also say hydronium is the conjugate acid of water. So conjugates are molecules that only differ by a proton, which is H plus. Hydrogen atom has a proton and an electron. So if you remove the electron and make H plus, all you're left with is a proton. So sometimes we call H plus ions protons. Okay. So in that second reaction, somebody tell me a pair of conjugates. Conjugate acid-base pair in the second reaction. Yeah. Yeah, NH3 and NH4 plus. They only differ by a H plus. And what's the other pair of conjugates then? Yeah, water and hydroxide, the other two molecules there. Okay. So we can see that in reaction, that we can pair those up as conjugate acid and conjugate base. So the next thing we want to do is be able to just figure out what the conjugate acid or conjugate base is of a given molecule without looking at it specifically in a reaction. We can set up a table like this. Where we look at some molecules, and let's just pick some here, like water, ammonia, we'll look at some others in a second. And we can say, what is the conjugate acid? All right. And then what is the conjugate base? So first, water. The conjugate acid, if we have to kind of come up with a rule for this. So let's go back and look at this. What happens every time we make a conjugate acid from a base? So if you look at any of the bases up there, and then look at its corresponding conjugate acid, what is different? What changes? But yeah. So going from the base to the acid, if we want to find the conjugate acid of something, we add H plus. So we add a hydrogen ion, H plus. And what do we do if we want to find the conjugate base of something? Look back up there at all those different reactions. What happens if you look at one of them that says acid on it and you want to find the conjugate base? What do you do to it? Yeah, take off one of those H pluses. Take off the hydrogen ion. So let's try that. What molecule do we get if we add H plus to water? H3O plus, right? And be really careful of the charges when you're doing this. So it's really easy to add or subtract an H. That's no big deal. But sometimes it gets confusing, or you forget that you also have to correct the charge. Because you're not just adding H, you're adding a positively charged H. So whatever you're adding to has to go up by +1 also. So it's not enough to just put the H there. What do you get then? So we're not going to go to the next column yet. Let's go down to NH3. What do you get if you add an H plus to NH3? Ammonium, right, NH4 plus. Okay, so now let's look over to the conjugate bases. We're making the bases from those original molecules, not from the acids, from the original molecules. So looking at water, if water loses H plus, what does it end up being? OH, and what's the charge? Yeah, -1, because if you lose a +1 hydrogen ion, that means that you're left with a -1, because you started neutral. We started with neutral water. Okay, let's do the next one. If we start with neutral ammonia and we lose a hydrogen ion, what do we get? NH2 minus, right? So we took away a hydrogen, we took away a +1. So we ended up with a minus. All right. Now you try a couple. And make them a little bit trickier for you. So that first ion, or I guess it's the third in the list, the first new one is bicarbonate ion. Then we've got hydroxide ion, and then methanol, which is a neutral compound. So see if you can find the conjugate acid and the conjugate base. And pay special attention to the charge. Make sure that you're getting the correct charge, adding or subtracting 1 to that. Here's the issue. It doesn't actually count, but anyway, but
Oh.
so do you want to, yeah, so do you have by the conjugate base? I think they'll have as much speed. We're not adding, we're not adding. All right, these are looking pretty good. So one thing that I'm noticing, everybody's doing fine with adding and subtracting the hydrogen as expected. It's adjusting for the charges that can get a little bit tricky. So imagine your charges are on like a number line. So if neutral is right in the middle, then you've got +1, +2, +3, and so on. And then the other direction is -1, -2, -3. Right, a regular line like that. So if you are adding H+, that means you're moving one position to the right on your number line. So every time you add a plus, you're going this way. And every time you lose a plus, you're going that way. So if you had a neutral compound, which would be right here, and you add a +1, add an H+, then you end up with a +1 charge. If you started with a +1 and you add an H+, then you get a 2+ charge. If you start with +2 and you add a plus, you get a +3 charge, and so on. Same thing going back this way with the opposite. If you're at +1 and you lose an H+, then you're at 0. If you're at 0, you lose an H+, you're at -1. If you're at -1, you lose a plus, you're at -2, and so on. So you're always moving one position on that line, either left or right, depending on whether you're adding or losing the H. So thinking about that, let's go through these. With bicarbonate, if we want the conjugate acid, we have to add H+. So that means that our molecule is going to be H2CO3 because we've added the H. And then we have to check our charge. We started as a -1, which is right here. If we added a plus, added an H+, then we're here. So that means that our H2CO3 should be neutral because we went from -1 this way to 0. All right, so then what should we get for our conjugate base of HCO3 minus? What's the conjugate base of bicarbonate? CO3 2 minus. So let's look at where we got that. Conjugate base means lose hydrogen ion, lose a proton. So that means that we are getting rid of the H and then adjusting the charge less positive because we lost a positive. So if we're at -1, we lost the positive, we're now at -2. So that should be -2. Okay, let's try the next ones. Hydroxide, if we add an H+, We did that one earlier. We're at water. So water is the conjugate acid of hydroxide. What do we get if we lose H plus from a hydroxide? Yeah, it's oxygen, but what's its charge? Yeah, so we got oxide here. So we once again, just like bicarbonate, if we start at -1, which is here, and we lose a hydrogen ion, then we've got to move the charge over one to the left and get -2. No, it doesn't matter. It's more commonly done with the number in front, but you can do it however you like. And then finally, methanol. This is a bigger molecule, but we're going to do it the same way. So we add a hydrogen, and then that's going to end up being positively charged. Anytime you start with something neutral and you add a +1, you're going to have something that ends up being +1 charge. And then the conjugate base of that is when we remove a hydrogen, and that gives us CH3O. And again, we have to correct that charge. So what should the charge be when we've lost a hydrogen? -1, yeah. So if we started neutral with methanol, we lose a hydrogen, we're -1. Yeah, Andrew.
How do you know where to put the H? I had CH4.
Yeah, good question. So why did I put it here versus here? The answer is it doesn't really matter. These types of compounds, organic compounds, we'll get into in the next chapter, and they're sometimes written a little bit differently, where they're spread out like that to show how things are connected. If you wrote that as CH4OH or CH5O or even or something like that, that would be okay for our purposes. Same thing with this one. If you took off one of these instead for here, that's all right. Usually with acids, we'll talk about in a second when we're talking about naming, the H either goes out in front or at the end, so that we can be really clear that this is an acid and something is going to happen with that H. All right. Questions about constructing conjugate acids and bases? All right. Let's move on. The next thing we're going to talk about is acid and base strength. So what do you think about when you think about a strong acid? It dissolves? Corrosive? Dissolves stuff? What kind of stuff? Yeah, whatever. Yeah, that's kind of a common, that's like our common everyday belief of like a strong acid is something that can like eat through tables and dissolve your skin and whatever, be really corrosive and dangerous. That's not exactly right. It's a really common problem because, like a lot of words, we have a use form in some, or a definition for them in some contexts and a different definition in other contexts. So when we're talking about acid strength in chemistry or in medicine or any kind of scientific context, and we say that something is a strong acid, what we're really talking about is the electrolytic behavior. So it doesn't actually have anything to do with corrosiveness or danger or anything like that. Or how it actually behaves. It refers to the fact that it's a strong electrolyte, which if we review that definition means that it breaks up entirely into ions. So something like HCl, which is a strong acid, if we take gaseous HCl and we mix it with water, we do this reaction that we just looked at. But because HCl is a strong acid, and this actually is a definitional thing, HCl is a strong acid. What happens in this reaction is it goes almost entirely to the right. In fact, so much to the right that we can assume it's all to the right. But just for illustration purposes, let's give a comparison of a backwards arrow. But we're saying that this reaction goes completely to the right. So that if you have a solution of HCl in water, you have a bunch of water molecules. You don't actually have any whole HCl molecules in that solution. All you have are hydronium and chloride. There are no whole HCl molecules in solution. So that's what makes HCl a strong acid. The fact that it completely breaks up into ions and makes a strong electrolyte. Okay, so let's look at what a weak acid would look like then. So weak acid means weak electrolyte where the acid doesn't really break up much into ions. A little bit, but not much. For example, here will be HF, hydrogen fluoride, which makes hydrofluoric acid. Same equation. Actually, let's leave the arrows out for now, so we'll see what happens. All right, so drawing these arrows in on a weak electrolyte means what? Are we going to have more ions on the right or more neutral molecules on the left? If it's a weak electrolyte, does that mean that when it's in solution, we have more molecules or more ions? More molecules, right, because it's the opposite. So that means that our arrows are going to look more like this. And we don't always draw them like big and little arrows like that. That's not like a thing. But just to illustrate what's going on here. Well, it's because of the difference in the behavior of the molecules. It's not necessarily something you can predict. There is a list of strong acids. There's about 7, I think, strong acids, and all the rest of them are considered weak. So let's look at how we would express this in solution. Same type of diagram. Now in this solution, we're going to have mostly whole HF molecules. It's still going to be dissolved, but it's mostly HF molecules, and then maybe a little bit of ions. A little bit of hydronium, a little bit of fluoride. Right. So now to compare those two acids, hydrochloric acid is a strong acid. Hydrofluoric acid is a weak acid. But hydrofluoric acid is a way more dangerous acid. The bottom one that is weak by its electrolytic definition is actually way more dangerous. That's like the kind of acid that you see in cartoons where if you spill it on the floor, it like eats through the floor and then goes down and eats through the next floor, and it can like dissolve your body. And you can't keep it in glass because it eats through glass. So you have to keep it in plastic or steel. So that's like one of those ones you don't want to mess with. I don't even think we have any in the department here, just because it's so dangerous. But it's still a weak acid. It's still a weak acid because of how it behaves in solution. So this is a really hard thing to keep straight. Anything that goes against what we've thought for our whole lives is really hard to wrap your brain around. So make notes to yourself, circle stuff, do whatever you have to do to try to keep straight that acid strength is about what it does electrolytically, does it form ions or not about is it dangerous or not, or is it corrosive or not. Yeah. Not really. These are all in solution. These are all particles in solution. No, not necessarily. They're just completely unrelated. So there's other aspects like concentration, how much actual acid is in the water, and just the behavior. So one of the reasons that HF is so dangerous has nothing to do with acid anything. It's because of the fluoride. Because fluoride can attach to silicon, which is what most building materials are made out of, like rocks and glass and things. And so it can break that up in a way that non-fluorine-based molecules can't. So they're just totally not related. But like HCl is also corrosive. If you get concentrated hydrochloric acid on your skin, it's going to burn you. It's not going to poison you and burn you, but it's going to burn you. But it's also the acid that we have in our stomachs. It just depends on concentration and where it's at and what can deal with it and what can't deal with it. Okay, so you think you can keep that straight with acid and base strength? All right, great.
Quick question.
Yes.
Like,
Yeah.
are we just supposed to know what are strong acids and weak acids, and then go from there? Like, they
Yes.
problem like that.
Yeah, so you don't have to, like, so let's say I said, is some acid strong or weak? There's no way you can answer that question without more information, because some acids are strong, some acids are weak, it's just how they're defined. So I wouldn't ask you that. But I might say, here is an acid that does this when it's mixed in solution and breaks apart at ions. Does that make it a strong acid or a weak acid? You'd say it's a strong acid because it breaks apart at ions.
Strong acid.
Yeah, there's strong electrolytes that form ions. So make sure you have those definitions of strong and weak electrolytes from the last chapter also, and then putting those together will help keep that straight. Okay. Let's talk about some acids you should know. First, as we said earlier, if you're given a specific reaction, you can look at what that molecule is doing in the reaction and determine if it's an acid or a base. That's what we just spent the first half of the class doing. So is it accepting hydrogens or is it donating hydrogens? That tells us about whether it's acting as an acid or a base. But sometimes you don't have that to look at. You don't have a reaction. So we can generalize a little bit and say that some molecules or compounds always or almost always act as an acid or a base. So let's look at some examples of that. Molecules that always act as acids or almost always act as acids are usually denoted as such by starting with an H. It's not always the case. There's examples in your book and stuff that we'll see in the next chapter where that's not the case. But a few of them that you should know for sure are HCl, which we call hydrochloric acid. We've used this in lab. We'll continue to use it in lab. It's an important one to know. There's also H2SO4, which is called sulfuric acid. Another strong acid that is commonly used, and I don't know if we've used this yet this semester, but we probably will. And then another common one is HNO3, which is nitric acid. So notice some similarities about those three. Those are all, by the way, on your objectives of ones that you need to know the names of. But you can see that each of them have an H or a couple H's out front. And then the rest of it is an ion that you know. So you know Cl as the chloride ion. You know SO4 2- as the sulfate ion. You know NO3 as the nitrate ion from the stuff we did before called ion names. So if you forget the formulas of these acids, one way you can put them together is by knowing the formula of the ion and then just adding enough hydrogens to balance out the charge. So you can think of nitric acid, for instance, on the bottom, as an ionic type compound of nitrate, which you know is -1, and then you add the H to balance it out, +1, -1. So you can think about it that way. It's not an ionic compound, it's a covalent compound, but it does produce ions in solution, and we can think about it that way to help remember the formulas. So if I asked you, what is the acid that's made from the phosphate ion? Or what is the formula that is made from the phosphate ion? What would the acid's formula be from that ion? Yeah, it would have to be H3PO4 because we know each H is +1. So if we have a -3 phosphate ion, the acid would be written as H3PO4, and that's called phosphoric acid. It's an important ingredient in some drinks, like especially Coca-Cola. So it gives it its particular, I wouldn't say particular flavor because it's got all kinds of flavors and stuff in it, but something that separates it from other things and makes it difficult to recreate at home. It also makes it a really good cleaning agent. I don't know if you've ever seen videos of like people cleaning stuff with Coke. You can clean metal really well because of the phosphoric acid. But a battery? Oh, on the top? Yeah. Yeah, so the phosphoric acid is really good at taking care of corrosion on metals. I can see that, yeah. I mean, no, it's not so much bad for your stomach because your stomach's so acidic anyway. It's bad for your teeth because it's got to go, to get to your stomach in the first place. All the stuff that it passes on the way to your stomach, it's not so great for that. But I mean, that's true with any strongly acidic beverage, which would include any juices or, like diet sodas or anything like that, which are also acidic.
What about like strongly acidic?
Yeah, same thing. So, your stomach can deal with those unless you have issues, but it's not great for everything on the way to your stomach. I think most dentists recommend for that. We'll talk about that a little bit when we get to pH, but the idea that if you're going to eat that stuff, like just eat it and then be done so that your teeth or your mouth can recover it from the acidity. And the worst is when you're like having a little bit of it throughout like a long period of time. So if you're like sipping a Coke or something for hours, that's not good because then your teeth are in that acid zone that whole time. All right, so anyway, we can look at acids like this. We can identify them by that hydrogen out front. How do we identify bases? Any ideas? We haven't really talked much about bases yet. So with bases, they are harder to identify. There's not as easy of a general rule of like the H is out front, it's an acid, if blank, it's a base. It doesn't really work like that. But there are some molecules that act as bases. So one of the most important components of bases is hydroxide ion. So wherever you see hydroxide ion, you can be reasonably confident that you're dealing with a base. So in a compound like sodium hydroxide or potassium hydroxide or calcium hydroxide, any of these ionic compounds that we've seen over and over again, those are bases. They're strong bases because they completely break up into ions in solution. Same definition as with acids. But we already know about kind of how they work because we've already talked about ionic compounds and what they do. Other non-hydroxide bases, you really have to see the reaction to know what they're going to do. So like one that we looked at earlier is ammonia, NH3. That's a base because, as we saw up here, when you put it in acid, it takes, or in water, it takes the hydrogen and becomes ammonium ion. It actually forms ammonium hydroxide, so there's your hydroxide right there. Ammonia cleaning agents like Windex, that kind of stuff, are really solutions of ammonium hydroxide. And the reason that you can smell them is that because this reaction goes mostly to the left, some of the ammonia reforms as a gas and kind of bubbles and comes out. You don't see the bubbles, but it comes out of solution, and that's what you're smelling with that cleaning stuff. But there are other basic compounds as well. Carbonates are basic. Many of the other types of metal ions are basic. There's not a great way to predict that, so we're not going to go through all of them. But if you see hydroxides, you can be pretty clear that it's a base. So let's look at what happens when these things combine. When you combine an acid and a base together, now we're not just talking about the roles of the reaction, but these things that are commonly acids or bases. They react and they usually do something common, which is form water. So if we take aqueous solutions of HCl and NaOH, which we're going to do in lab next week, and we react them together, they actually do what we might have called a double replacement reaction a couple chapters ago. So the H goes with the OH, and the Na goes with the Cl. And that makes water and sodium chloride. So our definition still kind of holds. The hydroxide takes the hydrogen, and the Cl is left. The only difference is the sodium ends up paired with those. But because we know how ions work in solution, where they're all separate, the sodium actually doesn't do anything in this reaction, because it was separate from the OH in the beginning, and it's still separate from the Cl at the end, because they're all dissolved in solution. So the only thing that really happens, so to speak, here is this OH grabs this H. So the H gets donated to the OH, which forms water. So the key to solving these reactions, or to be able to write equations for these reactions, is to notice that the product is going to solve water, or is going to be water. One of the products is going to be water. You can solve it from there. Let's look at what happens when we have a compound that has more than one hydrogen on it. So something like sulfuric acid, H2SO4. So based on the stuff we've talked about with conjugate acids, conjugate bases, we would say, all right, that sulfuric acid is going to lose a hydrogen. And become, so we form water. And we're going to lose a hydrogen and form HSO4 minus, which would then be NaHSO4. But that's not actually what happens, because when it's in that environment with sodium hydroxide, it's not just going to lose one hydrogen, it's going to lose all the hydrogens it can lose. So instead of just losing one hydrogen, the acid will actually lose all the hydrogens and become sodium sulfate. So the H2SO4 becomes Na2SO4. So in a neutralization, in this type of a reaction, acids are going to lose all their hydrogens, all their H pluses, rather than just one. So these acids that have multiple H pluses, like sulfuric acid, phosphoric acid, carbonic acid, are going to lose all of those and become whatever compound. And that means that the reaction has to be balanced a little bit differently. Once we do that, if we go back and look at the balancing, that means we have to put a 2 here and a 2 here to get it to work out. So let's try one of those, or let's try a different one. Write a chemical equation for the neutralization of phosphoric acid, H3PO4, by it's going to be a little bit different. Potassium hydroxide, KOH. So write a chemical equation for the neutralization of phosphoric acid by potassium hydroxide. Use what we just did as a guide and see if you can see how this one will work. All right, got some equations for this one? I looked around, it looked pretty good. So let's take a look at it. So to solve this, first of all, the keyword is neutralization, which tells us we've got an acid-base reaction that's going to form water as a product. Sorry. So that means we're going to react that phosphoric acid with potassium hydroxide. Okay. And then we'll form water as one product. And then our last product will be the other two ions, the phosphate and the potassium. So that makes the compound potassium phosphate, which by now you should be able to construct as K3PO4. PO4 is a 3- ion, which you know from the list, and so we need 3 Ks to balance that and make a neutral compound overall. Now we're not quite done because we are writing a chemical equation, and what's still missing from that chemical equation? Yeah, it's not balanced. So in order to balance it, we do our normal balancing thing, and we end up with a 3 here and a 3 here. So that's the complete balanced equation for that neutralization. All right, questions about that? You can do that maybe, a little practice.
So the H2 times 3 level 6, but what about that side?
So we got 6 H's on this side, and then on this side you've got 3 plus 3. Yeah, so 6 on each side. All right, let's think about the acid-base reaction that happens in pure water now, which is a little bit weird. It's called the self-ionization of water. All right, so this is a little weird, but imagine 2 water molecules doing an acid-base reaction together. So one molecule acts with the acid, one molecule acts with the base. Write what you get as products. Only one, I'll also tell you, only one hydrogen gets transferred in this process. So transfer one H plus from one hydrogen to the other, and what do you get? So let's do that. What do you get? Yeah. Yeah. So if we do that, we imagine one being an acid and one being a base, then we're going to get hydronium ion and hydroxide ion as the product. So the hydrogen goes from one to the other. Okay, so that's a little weird, but this actually happens in pure water. So water is not purely a non-electrolyte. A little bit of this happens just by water reacting with itself and forming these ions. But it's a tiny, tiny bit. So that means that when we draw our arrows, if we want to express that, we can kind of draw it like this, where mostly it's just water molecules, but a little bit is hydronium and hydroxide molecules. And we can actually measure the concentration of those. I'm going to introduce a new notation here. When we put these square brackets around a molecule, that means concentration of. That means we're talking about a concentration. So in pure water, the concentration of hydronium is measurable, and it is 1 times 10 to the minus 7 molar. That's pretty small. If we write that out, not in scientific notation, that's 0.000001 molar. So the amount of hydronium in pure water is that number of moles per liter. Right, that is not a lot of moles per liter. Very small number. And as it turns out, the concentration of hydroxide is also that same amount. So the concentration of hydronium in water is that small number. The concentration of hydroxide in water is also that small number. And we can generate something from there called the ion product constant for water. No, let's not talk about that. Well, sure. Okay, we'll do it. We're almost out of time, but we'll do it. There's a lot of different names of this. The book calls it the ion product constant for water. We can call it the equilibrium constant for water. The important thing here is the word constant. What does constant mean? Yeah, but what does it mean in terms of like a number? It's a number that doesn't change. So it's a number that is always that same number. And the number you get from the product of the hydronium and hydroxide concentration, which in this case would be 10 to the minus 7 times 10 to the minus 7, which is 10 to the minus 14. So that's a very, very small number, and it's not quite clear how that helps us, but we'll get into it next week. Basically, what this means is the product of the hydrogen ion concentration or the hydronium concentration and the hydroxide concentration always has to be the same number. So if you have two things multiplied together, and they always have to equal the same number, what does that mean when one of them goes up? Yeah. It's the opposite though. So if one goes up, the other one has to go down to compensate. Because they multiply together, they always have to be the same. So if one goes up, the other one has to go down. And that's what we're going to use when we talk about pH to figure out what these concentrations are. Because if we know one or we can measure one, then we can figure out the other one by doing this. So quick note in your studying this weekend. It will be helpful for this chapter if you review scientific notation if you haven't thought about it in a while. So this idea of like 1 times 10 to the minus 14th or 1 times 10 to the minus 7th If you haven't used that kind of notation in a while, you should go back and check it out. Make sure that you know what you're doing with it. I believe there's a review of it in the book on page 15. No, this will not be on the quiz on Tuesday, but this will be in the stuff that we do on Tuesday then going forward. So the quiz on Tuesday will be on the solution stuff. So we'll do a little more with solution concentration as well as osmosis and diffusion. And then the acid-base stuff we did today. So conjugate acids, bases, neutralization reactions, strong and weak acids and bases. On Tuesday, we will talk about pH, acidity, basicity, and buffers. And then we can definitively say that that is the end of the math in this semester. And then we get into organic chemistry and biochemistry.
Harder?
Harder? I don't think it's harder. You have to take that next semester? Which one?
Yeah, I think that's like the hardest chem you'll take.